list of changes and devices required to meet emission standards while maintaining acceptable drivability is getting longer each model year. Let's check off some of the emission control systems and units you'll find under the hoods of our 1974 models. This session is all about these emission control devices, what they are, how they work, and some important service suggestions. The PCV valve and fully closed crankcase ventilation eliminated virtually all crankcase emissions. I'm sure everyone knows how it works, but here are a couple of important service reminders. Check PCV valve operation every 12 months or 12,000 miles. If it's sticking, replace it. Do not attempt to clean it. It is also important to clean and lubricate the crankcase inlet air cleaner every 12 months or 12,000 miles. At the same time, clean the paper element of the carburetor air filter by blowing it out with air pressure. Replace the filter every 2 years. The heated intake air system is still a very important part of the cleaner air system. It must be properly maintained to provide good drivability and emission control. You've probably noticed the new oval-shaped air cleaner snorkels. This design reduces airflow noise. It also improves engine breathing because the oval shape results in smoother, less turbulent airflow. The evaporative control system, ECS for short, still uses a canister having 3 hose connectors. However, on some models, only the fuel tank vapor and purge hoses are connected to the canister. If the carburetor bowl connector is not used and is capped, you'll know that the carburetor for that engine has an internally vented fuel bowl. The only periodic service required on the evaporative control system is replacement of the canister filter element every 12 months or 12,000 miles. Incidentally, this is the new look in fuel tanks. The vapor-liquid separator is located in the domed portion of the tank. Next, let's take up oxides of nitrogen. You'll remember that NOx emissions are caused by extremely high combustion chamber temperatures. So the way to control oxides of nitrogen is to reduce the peak temperatures generated in the combustion chamber. That's where the EGR system comes in. The exhaust gas recirculation system dilutes the air-fuel mixture in the intake manifold with controlled amounts of exhaust gas. Since exhaust gas contains little or no heat-producing gas or particles, it reduces NOx formation by reducing combustion temperature peaks. On the 1974 models, you'll find some modifications in the EGR system. All engines now have an EGR control valve. On some models, ported vacuum is used to open the EGR valve. The vacuum source is a slot or port in the throttle body located just above the throttle valve. At closed throttle, very little vacuum is applied to the EGR valve. The amount of vacuum increases in proportion to throttle opening. On other models, Venturi vacuum rather than ported vacuum is used to control the EGR valve. Variations in Venturi vacuum very closely match changes in the amount of exhaust gas recirculation required to control NOx. However, Venturi vacuum is not strong enough to open the EGR valve. So the Venturi vacuum signal is routed to a vacuum amplifier. The amplifier is actually a proportional vacuum regulator. It uses the relatively weak Venturi signal to control the amount of manifold vacuum applied to the EGR valve. You'll find a detailed explanation of both the ported vacuum and the Venturi vacuum EGR systems in Tech Session 73-1. To bring you up to date on the 1974 models, let's take a closer look at the EGR time delay feature and the new CC EGR valve. You'll find a new coolant control exhaust gas recirculation valve on the 1974 models. The official name for this valve is quite a mouthful, so it's been nicknamed the Kager valve. This is the new 1974 Kager valve. And this is the coolant temperature control valve found on later production 1973 models. The two valves look alike, but are quite different in construction and operation. This late production 1973 valve is actually a vacuum bleed valve. When the engine and coolant are cold, the valve opens, and bleeds air into the EGR system. For all practical purposes, this is simply an air leak which keeps vacuum from building up enough to open the EGR valve. When the coolant warms up, the valve closes, so the system is no longer vented. Normal exhaust gas recirculation goes into operation. So remember, this valve has an air inlet filter and only one vacuum hose connection. The new Kager valve has two vacuum hose connections. This is a flow valve, not a bleed valve. It is connected in series into the EGR vacuum control line. Unlike its predecessor, it is closed when the engine and coolant are cold. It does not open until the engine coolant warms up. As a result, the new valve is the fail-clean type. If the valve should leak for any reason, it will not reduce the effectiveness of the NOx emission control system. Incidentally, this is the latest type 1974 Kager valve. Although it looks entirely different, it works exactly like the one we've been talking about. So don't be surprised if you see one of these Kager valves in the top tank of the radiator. Here are the EGR time delay units, the EGR delay timer and the EGR delay solenoid. They are used on some models in addition to the Kager valve as part of the NOx control system. These two units work together to delay exhaust gas recirculation for approximately 35 seconds after the engine is started, regardless of engine coolant temperature. Here's how they work. The EGR delay timer is connected to the ignition run circuit. As soon as the ignition is turned on, the timer completes a circuit to the EGR delay solenoid. Energizing the delay solenoid closes a built-in vacuum valve. This shuts off the control vacuum to the EGR system. After 35 seconds, the timer opens the circuit to the solenoid. The vacuum valve opens and the EGR system goes into action. The EGR system should be inspected and operation checked every 12 months or 12,000 miles. Inspect all hoses, hose connections, and make sure the entire system is free of vacuum leaks. The engine should be warmed up before testing the EGR valve. Quickly increase engine speed from idle to 2,000 RPM while keeping an eye on the EGR valve stem. The valve stem should move as the engine is speeded up. Here's an easy way to make sure exhaust gas is actually flowing through the valve and into the intake system. With the engine idling, apply manifold vacuum directly to the EGR valve. Engine speed should drop off at least 150 RPM. The engine may stall as the valve opens. The engine should speed up as vacuum is removed, closing the valve. Next, let's review the basic operation of the OSAC system and take a look at the 1974 version of this part of the NOx control system. To begin at the beginning, it's a fact that combustion chamber temperatures tend to increase if normal spark advance is permitted during acceleration. Since high temperatures increase NOx emissions, these higher acceleration temperatures must be controlled. The heart of the OSAC system is an orifice-type vacuum valve. It is connected in series between the carburetor vacuum port and the distributor vacuum advance diaphragm. During acceleration from idle to cruising speeds, the OSAC valve delays the vacuum buildup required to provide full vacuum advance. This brief delay reduces combustion chamber temperature peaks that normally occur during acceleration. On many 1974 models, the OSAC valve is located in the air cleaner, and its operation is controlled by the temperature of the air entering the carburetor. On these models, the OSAC valve orifice is bypassed in very cold weather during warm-up, resulting in normal vacuum advance. This improves cold engine drivability. As soon as the intake air reaches about 50 to 60 degrees, the thermal control built into the valve routes vacuum through the OSAC valve orifice. The orifice restricts vacuum buildup during acceleration, and the resulting delay in vacuum spark advance reduces combustion temperature peaks, and hence NOx emissions. Delaying spark advance could cause engine overheating under severe low-speed operating conditions. This could result in increased hydrocarbon emissions and, in extreme cases, could result in engine damage from overheating. To protect against this, some OSAC systems are equipped with a thermal ignition control, referred to as a tick valve. Here's what it does. When engine coolant temperature reaches about 225 degrees, the tick valve opens and full manifold vacuum is applied to the distributor vacuum advance unit. This increases engine speed and cooling. As soon as the engine coolant drops, normal OSAC operation is restored. The OSAC valve and related plumbing should be inspected and tested every 24 months or 24,000 miles. Use a vacuum gauge to check overall operation of the system. With engine warmed up and running at 2,000 RPM, connect the gauge to the OSAC valve in place of the distributor vacuum advance hose. If the valve is operating properly, the vacuum will increase slowly until it registers manifold vacuum. This should take about 20 seconds. The exact time will vary with different car and engine models. If vacuum pops up immediately, the valve is open and not metering vacuum. If vacuum does not build up, the valve is plugged, is not opening, or perhaps one of the hoses is disconnected or leaking. On models equipped with a tick valve, be sure it's okay before replacing the OSAC valve. You'll find complete instructions for testing it in the reference book. The new two-stage electric assist choke helps match air-fuel mixture more closely to engine starting and warm-up requirements. Actually, the electric heating element reduces hydrocarbon and carbon monoxide emissions by speeding the opening of the choke. The big change is not in the choke, but in the new dual-stage control switch. This switch reacts to changes in intake manifold temperature. When the temperature is lower than about 58 degrees, a resistor in the switch reduces the voltage applied to the choke heating element. This low assist stage helps open the choke and compensates for the elimination of the manifold heat control valve. When the manifold is warmer than 58 degrees, the control switch bypasses the built-in resistor and sends full battery voltage to the choke heating element. This speeds up the dechoking assist and shortens the time the choke is on. At approximately 110 degrees, the control switch opens the circuit to the choke heating element. And that brings us to the 1974 carburetors. As you probably have heard, many of them are now of the solid fuel type. However, detailed information on the new carburetors will have to wait for another Master Tech session. This month's reference book has additional information on ignition, choke, fuel filters, and other periodic service required to keep those 74 models clean and drivable.